Hello, my name is Kayla Ruttan and I'm from Clarkson University. Today I will be presenting on thermal simulation for GPGPUs. Due to their vast parallel computing capabilities, and increased demand has emerged for the usage of general-purpose graphic processing units. However, temperature increases have led to a degradation in performance and reliability. Since the beginning of IC technology, thermal simulations for semiconductor chips have been modeled from lumped RC thermal circuits, and there is no known thermal simulator specific to GPGPUs. We are currently developing a thermal simulation approach that will work for GPGPUs at the architectural level in order to improve the efficiency and accuracy of the conventional RC method. We have decided to start our project with a CPU and will eventually make this work for GPGPUs. The open source code utilizes a finite element method to solve the heat conduction equation and to collect thermal data. The structure of the CPU and the dynamic power maps are generated, which represent the average local power dissipations induced by electrical signals in the CPU. The figures below show the generated thermal data of the chosen semiconductor chip. The temperature map of the simulated CPU is displayed here in Figure 1. You can see here we have blue and yellow regions. This is where the hotspots are located. In Figure 2 is the corresponding floor plan, where A, B, and C indicate the locations of the power sources within the chip, which create the hotspots here in Figure 1. The temperature and power density along the X and Y direction cut lines, here in the blue, are presented down here below in Figure 3. The red line is power density and the blue lines are temperature. You can see here, this is the x-axis cut line where it crosses through C and B, and the y-axis where it crosses through C and A. Data is also collected to show the maximum temperature and power density over the simulation time. Figure 4 shows the maximum temperature over time. Here you can see that the blue line is C, B, and red line is A. Figure 5 provides the maximum temperature data along with the power density. The red line again is the power density and the blue is temperature. This approach utilizes proper orthogonal decomposition, a projection-based learning algorithm to train the modes of the thermal data from the GPGPU. Unlike other machine learning algorithms, such as PCA and SVD, which predict static behaviors, POD modes capture the true transient dynamic behaviors of the system by further projecting the heat conduction equation onto the POD space. In order to train the POD modes effectively, a massive amount of good quality data is needed. A set of ordinary differential equations are then created for this variable, shown here, a sub I of t, using the POD modes together with heat conduction equation. This method prevents making assumptions about the dynamic temperature progression, and the model produced is very effective for these thermal simulations. One disadvantage to this approach is that the model development is very time-consuming. The process of data collection from the finite element or finite difference simulation, generation of POD eigenvalues and modes, takes a great amount of time to complete. This is due to the massive amount of data being collected and processed to produce the model parameters. Further computation must also be done on the data using the spatial POD modes during the calculations of the POD model parameters. Due to the large amounts of data being collected and processed, the development of the model is very slow, and speeding up this process is crucial. Implementation of MPI. To overcome the substantial time consuming of the POD model development, MPI, or message passing interface, is being used to decrease the computing time. MPI will be utilized in generating the POD modes and eigenvalues, also to evaluate the POD model parameters. The program, written in the C language, utilizes Portable Extensible Toolkit for scientific computation, also known as PETSI, as well as SLEPSI, the scalable library for eigenvalue problems. PETSI is a suite of open source software libraries for parallel solution of application modeled by PDEs, and the SLEPSI extension enables the solution of large-scale sparse eigenvalue problems. PETSI itself employs the standard MPI for its parallelization. This is utilized for the computation of the POD mode and eigenvalues during the thermal training. Additional research is being done with MPI application for single block POD model parameter calculation to determine how much time can be cut off from execution using different numbers of cores. Also to determine other ways MPI can be implemented in the program, which will be extremely important when determining the effectiveness of parallel computing in multi-block approach. The multi-block approach utilizes domain decomposition. When evaluating a large structure, the amount of data to be processed becomes much greater, as seen in the structure of a GPU. Therefore, MPI may not provide sufficient speedup, and thus domain decomposition is applied due to its natural advantage for effective parallel computing. This method is applied to divide the structure of a semiconductor chip into small generic blocks, representing caches, streaming multiprocessors, cores, or functional units, more. Each block domain is projected onto a set of POD modes and then joined to construct a model for the entire chip. It is much more efficient to train POD modes and generate model parameters for these smaller blocks than to compute for the whole chip, thus saving computing time. A large structure will therefore be made up of numerous generic blocks. To minimize the simulation time during the prediction of the temperature in the semiconductor chips, MPI will be used again to perform the POD simulation to further increase efficiency. If high-resolution simulation is needed, this also increases the amount of data required to be processed, resulting in more time-consuming simulations. To make the generation of the POD modes and evaluate the model parameters for the multi-blocks more efficient, MPI will be applied once again to further increase efficiency. Thank you for listening to my presentation.